So the next KSP is हमने we did past paper questions, right? मतलब इसके you don't have a lot of KSP questions, but I think I do remember doing KSP questions. किए थे ना?
Yes, sir.
अच्छा, so but let's try and do a few more. Just a second. The only problem is because there are very few questions. एक second, it was before topical. Just the common and effect questions. One second. अच्छा नहीं, these ones we. ठीक है, if I'm able to find just one second. Nee, that's a simple KSP question, common and effect. So this one is interesting. ये कर लेते हैं start one. So you think KSP of Ag2S, ठीक है? So let's try and do this quickly. It will dissolve and it will produce what? It will produce two silver ions and one S2 minus ions, aqueous, right? All of them aqueous ions. What is your KSP expression? That's Ag plus 1 concentration squared, okay, into S2 minus 1 concentration. Okay, that's what your KSP is. He said that the solubility of Ag2S is given as 1.16 times 10 power minus 17 mole per dm cube. So calculate the numerical value for KSP. The solubility is the amount of substance that dissolves. So if it's x mole per dm cube, the amount of silver ions would be 2x, and the amount of sulfide ions would be x. Okay, according to the ratio. So if the solubility is x, so the ions would be 2x and x, right? So your KSP expression would become 2x squared times concentration x, right? And that is equal to what? 4x cubed? यही होगा ना? Is that clear? And
Yes,
Yes.
sir.
ठीक है, and the value of solubility is given. ठीक है, that's 1.16 times 10 power minus 17. So I'm just going to plug that in. So it's 4 times what? 1.16 times 10 to the power minus 17, and that's going to be cubed. So what are we getting? What's the answer? You clear it? X was the solubility, right?
6.24 multiplied by 10 to the power minus 51.
ठीक है, so that means it's very, very insoluble. ठीक है, 10 power minus 51. Uh, and the unit would be mole cubed, dm minus 9. ठीक है, concentration squared into concentration. Now, the next part is calculate the minimum volume of water needed to dissolve 1 gram. So what's the minimum volume of water that's needed to dissolve 1 gram of silver sulfide? So this is the amount that I need to dissolve. So first thing, what is the solubility? He's given us the solubility. So what is the amount of silver sulfide that dissolves in water in 1 dm cube? So it's 1.16 times कितना 10 power minus 17 moles dissolves. Mole per dm cube means this is the amount that's going to dissolve in how much water? In 1 dm cube. ठीक है, is this clear? That we got the solubility and that's the amount that dissolves in 1 dm cube. So I need to figure out if I want to dissolve this amount, how much water do I need? So I'm going to convert that into moles first. The mass divided by molar mass. So 1 gram divided by what is the molar mass of Ag2S? EGK, I think it's 108. You could confirm कर ले.
Yes, sir. 107.9.
ठीक है, so 107.9, ठीक है. Times 2 and sulfur is 32.1. Let's take it as 32. I mean, you should take it as 32.1. यहाँ पे I'm just doing this quickly. So how many moles do I get?
4.03 multiplied by 10 to the power minus 3.
So I'm going to try and figure out if I want to dissolve these moles, how much water do I need? So it's going to be the same ratio, right? So what do we get? It's you just do crisscross and X would come out to be it's going to come out to be 4.03 times 10 to the power minus 3 divided by the whole thing 1.16 times 10 to the power minus 17. So what are we getting?
3.476 multiplied by 10 to the power 14.
3.476
Yes,
dm cube,
10
right?
power 14.
So that's a lot of water needed just to dissolve a tiny amount of. I mean, that's like a lot of water, okay? Well, probably that's probably going to be like an ocean of water, right? Okay, that's a lot of water, 10 power 14 dm cube. So that's a lot of water, okay? So 1 gram that shows okay, it's very, very insoluble. Okay, so even 1 gram, it's very hard to dissolve. You need a lot of water to dissolve that. You clear? Is this question clear?
Yes.
Okay, this was not a common iron question. एक second, let me just make one effort. ठीक है, but I'll send those questions separately as well. But we did one example of a common iron question. The remaining we already did. ठीक है, so we're gonna move on. अच्छा, the next part, ठीक है? The next part is it's called KPC. अच्छा, it's got nothing to do with the equilibrium constants that we studied already. So it's completely independent of the others. So this is known as partition coefficient. ठीक है, that's what KPC is. अच्छा, KPC is also like KSP. You just get, I mean, you mainly get two types of typical questions on KPC. So KPC is it's let me write the definition. They're going to ask you for the definition as well. So it's the ratio of the solubility of solute of a solute in two different immiscible liquids. ठीक है, that's forget what it means right now. That's the definition. That's what you're going to write when you talk about KPC. Let's try and understand what KPC is. So if I have first thing, you need two immiscible liquids, right? So if I have a beaker and it's got two immiscible liquids, it's got let's say it's got hexane, which is basically oil, and it's got a layer of water. Now they're going to form because they're completely insoluble in each other, so they would form two separate layers. और ये जो middle part है, that's the division. That's known as your partition. So there's going to be a boundary, and that boundary would be separating the two layers. ठीक है, that's what your partition is. Now I'm going to try and mix a solute into this mixture. It is a mixture, but they're not mixing with each other. So if I try to mix, let's say I mix NaCl into this, and what's going to happen is NaCl would mix. NaCl, so NaCl, would it be more soluble in hexane or would it be more soluble in water? Okay, well, what do you think?
What?
ठीक है, it's probably going to be more soluble in water, right? Because Na ions are positively charged and Cl ions are negatively charged. So they've got polarity, right? So polar things would mix in polar substances. So you're going to see, like, if you mix it with a spoon, the layers would not mix, but NaCl, most of the NaCl would probably go into it will probably go into the water layer, right? ठीक है, but it's not going to be very soluble in hexane. But since it's not being soluble doesn't mean that there's absolutely not going to be any NaCl in hexane. It just means low solubility. So maybe there's a couple of particles in the hexane layer as well, right? So is this clear? This idea clear that when you dissolve NaCl, most of it dissolves in water and very little of it dissolves in hexane. Is that clear?
Yes.
ठीक है जुहेर clear है? Zain, is this clear?
Yes, sir. Sure.
अच्छा, now so the reason we study this is because a lot of your I mean, like the human body, okay? Human body has a lot of partitions. There's a fat layer, there's a water soluble layer. So, so everywhere you go, I mean, there might be blood flowing over here, there might be a fat layer over here. So the reason partition, I mean, this idea is important is because in a lot of real world scenarios, you don't have one liquid, you have a mixture of liquids, and they are probably not soluble in each other, which is why they have a lot of partitions in between them. Now, this is the current picture. But the thing is, it's a dynamic system. What that means is that the particles of NaCl will constantly be crossing the partition because they're not stationary. I mean, this particle over here is kind of randomly moving around, right? So maybe it might cross the partition and might end up in the hexane layer. That hexane layer particles NaCl would be moving around and they might cross the partition and might move into the water layer. So it's a dynamic system, which means that particles are constantly moving around, right? So particles are moving from the water layer into the hexane layer and from the hexane layer back into the water layer. Now, if both rates are equal, like if two particles move into the hexane layer per second and two particles move from the hexane layer into the water layer, then the concentration of the particles in both layers that would remain exactly the same. And that would mean that there's an equilibrium that's established at the partition. Is that clear? So what you
सर लेकिन नंबर ऑफ पार्टिकल सेम रहेगी वाटर में और ऑक्सीजन में.
name, like if two particles, let's say two particles cross into in 1 second, two particles cross into the hexane layer. And at the same time, two particles of NaCl cross from the hexane into the water layer. So then when something is at equilibrium, the concentration of the particles does not change. Is that clear?
Yes.
So I can write this as a reversible reaction where I've got NaCl in water and it's in equilibrium with NaCl in hexane. Right? Is that clear?
Yes,
So
sir.
so that's it. Okay? So basically KPC is the Kc for this reaction. What is the Kc? I'm going to call it KPC. It's the concentration of products NaCl in hexane. So concentration of NaCl in hexane divided by the concentration of NaCl in water. You can just write it aqueous. Okay, so that's it. That's what KPC is. So that's it. That's what KPC is. So whenever you have a partition and there would be a solute that's mixed into the mixture. So there would be some solute over here, some solute over here, and eventually the solute would reach an equilibrium. Particles would be crossing the partition. So the particles moving from top to bottom and the ones moving from bottom to up. I mean, the rate would be exactly the same. So which is why they'll have an equilibrium established, and the equilibrium constant for this particular equilibrium is known as the KPC. So your definition was that it is the ratio of the solubility of a solute. So it's mole per dm cube, mole per dm cube. So the solute concentration in two different immiscible liquids, in hexane and in water. So it's the ratio of that. Is that clear?
Yes sir,
Yes,
सही.
sir.
ठीक है. अच्छा, so that's what one second. Okay, so that's what KPC is. Now, the idea of KPC is that if it's got a large value, normally in KPC, um, the way you write KPC, this is going to be written as it's the KPC calculated because the problem is which one is the product, which one is the reactant? Because you could have written it the other way around as well, right? So if I had written NaCl water on the other side, NaCl hexane on this side, then my this would have been inverted, right? The numerator would be the denominator and so on. So the way to remember this is that if they write calculate the KPC between calculate the KPC for NaCl between hexane and water, right? Then make sure that the layer that appears first, like if they write hexane first, that's the numerator. Okay, the first one is going to be the numerator, and the one that they refer to as like the one that comes later on, that's going to be your denominator. Okay, is this clear?
Yes.
So if they had
Yes,
written
sir.
if they had written KPC for NaCl between water and hexane, then you would have switched it. Then the whole equilibrium you would have written it the other way around. Okay, so keep that in mind. Acha, so you've got so how do you so you're going to get two types of questions. The first type of question is that you calculate KPC. That's the first one. So simple reaction, calculate KPC. So what they're going to state is that acha, one other thing. The thing with KPC is what is concentration? It's mole per dm cube, right? And this one is also mole per. I mean, concentration is mole per dm cube, right? What is moles? Moles is mass divided by mr per dm cube, right? So moles would be mass divided by mr over dm cube, right? Now this thing is that the mr is going to be the same because it's NaCl and NaCl over here as well. So there's no need for dividing it by mr. You could directly use mass. So often KPC, I mean, you're going to use concentration, but that could be simplified further to just gram per cm cube. So instead of mole per dm cube, you can use mass per cm cube, mass per cm cube. Because the MR would get cancelled out anyway. So dividing by MR, calculating moles of NaCl in water, that would be irrelevant because the MR part would get cancelled out because both of them are NaCl. Is that part clear?
Yes.
Yes, sir.
And even converting the CM cube to DM cube is like irrelevant because you divide by 1,000 at the top, you divide by 1,000 at the bottom. That's irrelevant because divide by 1,000, that would get cancelled out as well. So you don't need to convert that. So what you can do is you can simply find gram per cm cube, gram per cm cube. You don't have to do a lot of working for this. You can directly put in gram per cm cube, divide by gram per cm cube. So if I have a question, so let's find the KPC for this one. There is, let's say, 1 gram of NaCl over here, and there is 10 grams of NaCl in water, right? The volume of water is, let's say, 500 cm cube, and the volume of hexane is, let's say, that's 50 cm cube. Okay, let's take that as 200 cm cube. So can you calculate KPC? And remember, I'm going to tell you KPC between, for the above case, between hexane and water. So the KPC would be, for hexane, it's going to be 1 gram divided by what, 200? Or niche bottom pay, it's going to be 10 grams divided by 500, right? The hexane has to be on the top because it's coming first, and water has to be at the bottom, right? So what is the value that we get for this? What do we get?
1 by 4.25.
Okay, so we're getting 0.25. If you have a low value of KPC, that indicates that the substance is more soluble in the denominator layer, right? So smaller value indicates more solubility in the layer that appears in the denominator and vice versa. So now the second type of question is that they'll give you KPC and you would have to figure out the reverse. So the second type is KPC is given. So we already know what the KPC is. So KPC is 0.25. So the question is find the amount of NaCl extracted if 20 cm cube of hexane is added. Okay, remember we already calculated KPC and KPC is a constant. Now KPC is always going to be a constant between the hexane and water layer. For some other partition, it's going to be a different value, but for this particular case, hexane and water, it's a constant. No matter what the concentration is, no matter what, the only thing that changes it is temperature. That's it. Okay, just like any other equilibrium constant, only changes with temperature. So as long as it's hexane and water and there's NaCl being added, no matter what amount of NaCl is being added, no matter what the volume of hexane and what the volume of water is, KPC would always be a constant. So the question is find the amount of NaCl that's extracted if 20 cm cube of hexane is added to 400 cm cube of water, which contains uh let's say 8 grams. Okay, so here's what the question is. Remember, we already know what the KPC is. So it's a slightly different mixture. So you've got 400 kitna cm cube water. That's 400 cm cube water, right? So I've got this much water, and the water already contains 8 grams of NaCl. Now he's saying what is the amount that's going to get extracted or removed? What is the amount of NaCl that's going to get removed if I add 20 cm cube of? So if I add 20 cm cube of hexane. So the question is, how much of the NaCl would go into the hexane layer? Because there's obviously going to be some of the NaCl that's over here that's going to travel, and it will cross the partition and it will end up in the hexane layer, right? I don't know what the quantity is, so I'm going to take it as X grams. Tika, right now I have no idea what is the amount that's going to go into the hexane layer. So what is the amount that's left behind in the water layer? क्या होगा if X grams goes into the hexane layer, what is the amount that's going to be left behind? Okay, anyone?
8 minus x.
ठीक है 8 minus x ठीक है so now the amount that's left behind is 8 minus x grams, right? And eventually it's going to reach equilibrium, right? So the point is, you had 8 grams of NaCl over here, and a tiny amount of NaCl went into the into the other layer, right? That's x grams. So the amount that's left at equilibrium is 8 minus x, which is time we did this thing in the original KC as well. That a tiny amount goes into the product, so you're left with 8 minus x, right? So I'm going to calculate the KPC. The KPC we had was the hexane was the top layer, right? The hexane was the numerator and the water was the denominator. So we got 0.25. So I'm going to try and calculate the KPC for this. The KPC would be for hexane, it's x grams divided by 20. And at the bottom, I've got water, which is 8 minus x divided by 400, right? And the KPC value is what? It's 0.25. I'm going to try and solve this and I'm going to try and find out what. So we need to find out what x is. So what we are going to have is it's going to be x over 20 times 400 goes up and 8 minus x is in the denominator. So 2, how many times? 2. So I'm left with 20x. So basically it's 20x divided by 8 minus x, and that's equal to 0.25. And we solve for this. So 20x, 0.25 into 8, what is that? That's 1 over 4 into 8, that's 2.
Yes. 2.
ठीक है, minus 0.25x, right? And then solve this further. So it's 20.25x is equal to 2, right? So what do we get x? What is the value of x?
0.0988.
So it's coming out to be 0.0988 grams, right? So that is the amount of because remember I added a very little amount of hexane, right? So that is the amount of NaCl that went into the hexane layer. ठीक है, is this clear? This one, like if they give you KPC, so you can calculate the reverse as well. ठीक है, is this clear?
Yes.
Yes, sir.
So that's it. KPC, you get two questions. You either have to calculate KPC or you have to figure out ऐसे इसका मैं let me just so we're gonna do some KPC questions now. As a KPC questions are like very rare. Just one second. Let me ठीक है, let's try this topic. ठीक है, here's one. As a KPC, define the term that's why I wrote down the definition. It's the ratio of the solubility of a solute in two different immiscible liquids. ठीक है. Now this one. Again, this is, I think, the reverse question. ठीक है, I can't write on this. Just one second. I said this is kind of the reverse question because they gave us the value of KPC, right? That is already known. So a solution of and the KPC is between two solvents. One is octane one all and the other one is water. So I've got octanol and water. ठीक है, so there are two separate layers. There's octane 1-ol, and the other layer is your water layer. Now, what is the amount of octane 1-ol? That's 25 cm cube. So I know the volume. What is the amount of water? That's 125 cm cube. Now, a solution of zero point 0.4 grams of benzoic acid. Benzoic acid, remember, is probably the solute that you're adding. So he's adding 0 0.4 grams of benzoic acid to this. Calculate the mass of benzoic acid extracted into the water layer. So what amount of benzoic acid goes into the water layer? So if I say that X grams goes into the water layer, so what is the amount that's going into the octanol layer? Okay, okay, what's the number?
X minus 0.4, 0.4 minus X, something like that.
Okay, so it's going to be 0 0.4 minus X grams, right? So if you're mixing zero point 0.4 grams, X grams goes over here, so the remaining that's left is zero point 0.4 minus X. Is that clear?
Yes, sir.
As a plus,
Yes, sir.
the way he's written it, kpc of benzoic acid between this and this, the octane 1-ol layer is the numerator and the water layer is the denominator. So I'm going to calculate the kpc. So it's zero point 0.4. The octane 1-ol layer is the numerator, zero point 0.4 minus X, divided by what, 25, and divided by what, it's X divided by 125. And the answer we already know, that's 79.4. So I'm going to first rearrange all of this. It's zero point 0.4 minus X, 25, and on the other side it's going to be 125 divided by X. The 25, this would be 5, I think. So it's going to be 5. Let me try and solve this. 5 into zero point 0.4.
2x over x.
नहीं, 0.4 minus X into 5 करो ना, that's
Oh, okay.
what's 5 into zero point 0.4? 5 into zero point 0.4, I think is 2, right?
Yes, 2 minus
Yes,
5x.
sir. Yes, sir.
So I think that's 2 minus 5X, right?
Yes.
And at the bottom you've got an X, and then this is equal to the answer 79.4. So take that X over there, take the 5 on the other side as well. So what do we get for X? 2 divided by what is this whole thing? That's 79,
84.4.
84.4. So how many grams is that?
0.02.
Okay, so the answer is 0.02 grams. Is that clear?
Yes, sir.
Sir.
Yes, sir.
So now the next part. Now this one, they often mix KPC with the intermolecular forces as well. Like in the next part. See, this is benzoic acid, right? And you gotta, let me remove this 1 second. Okay. Now he says KPC of benzophenone. That's another substance. Between octane 1-ol and water is different from the value of KPC of benzoic acid given. Explain why. So this is benzophenone. So it's a simple question. It's a 1 mark question. Why do you think it's the other substance? If you change the solute, why does that have a? So it's more like a general answer. It's just a 1 mark question. Why do you think benzoic acid has a certain value for KPC? Why does this other solute have a different value for KPC?
Maybe because they make different bonds with water, like because of their
Uh, th-
solubility.
they've got this one has got a it's got different intermolecular forces, right? So that's it.
Yes.
So this has to do with solubility, and let me explain this. Balki, let's make the question more complicated. Let's make it a 3 mark question. Can you tell me whether the KPC of benzophenone would it be higher than the first one or lower than the first one?
I think it would be higher.
So let's start with benzoic acid, right? So you have octanol, you've got two layers, right? You've got octanol and you've got water. Which one do you think is more polar and which one is less polar? Which one has more van der Waals forces? Which one has more hydrogen bonding?
So water has a more hydrogen bonding.
ठीक है. So water is highly polar, right? It forms hydrogen bonds, and that means it's very polar, right? So what is the rule for? So what is octanol? Octanol is mainly a carbon chain. It's like eight non-polar carbon atoms, right? So so most of octanol is non-polar. There's a tiny bit at the end which is polar, but that's just a tiny bit. So percentage-wise, octanol is mostly is mostly van der Waals forces, right? Most of the carbon chain is non-polar and it's forming van der Waals forces, and it's going to be completely non-polar. Okay, so compared to water, this is very, very non-polar. Is that part clear as well?
Yes.
Yes, sir.
Acha, so sorry. Acha, so this is relatively speaking, this is how do I remove this? So relatively speaking, okay, एक second. So no idea how to grab this. Acha, relatively speaking, this is non-polar, right? Acha, benzoic acid, do you think that's polar or non-polar? It's got a carboxylic acid group. Well,
Sir is polar.
it's polar, right? It's got double bond ON, OH. So in which layer would more benzoic acid would be found? Would it be found in the water layer or would it be found in the octanol layer?
Octanol?
Hmm? You see, it's polar, right? It's also capable of forming hydrogen bonds, right? So, but more benzoic acid would be found in the water layer compared to the octanol layer. Is that clear?
Yes, sir.
Yes.
Now compare this, and this is just relatively speaking. I don't know what is the ratio going to be, but my hunch is that benzoic acid is capable of forming hydrogen bonds. So you're going to find more of it in the water layer and less of it in the octanol layer, right? Now here's this other substance. Do you think this substance forms hydrogen bonds? But it doesn't have an OH group, right? Do you remember that you need an OH to form hydrogen bonds?
But sir,
Yes, sir.
it had
The hydrogen
point
bonding.
O.
No, like it doesn't form hydrogen
Yeah,
bonds.
yeah, it does not.
So that means compared to benzoic acid, it will be less soluble in the water layer. Is that clear?
Yes, sir.
Yes.
So
Sir.
compared